So, getting back on track, let us now look at series, um, since we have seen some amount of sequences. Okay. Um, every sequence that we will look at now is going to be complex valued unless I specifically mention otherwise. Okay. So, um, if I say sequence and it's going to be a sequence of complex numbers unless I specify, oh, it's a real valued sequence. So definition. Given a sequence an, we use the notation summation n is equal to p to q of an to denote the sum to denote the sum an is equal to ap plus ap plus 1 plus dot 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 aq, right? The standard notation. And with an, with the sequence an, we associate another sequence Sn, which is called the sequence of partial sums, called sequence of partial sums, where Sn is equal to summation I is equal to 1 to n ai. Okay. This short, another notation for Sn is for Sn we use the notation of I is equal to 1 to infinity ai, or n is equal to 1 to infinity ai. Okay. The final one is called a series. Okay. This is called a series, and it's generally an infinite sum, or so it's called an infinite series, or generally just a series. Sn are called partial sums. Okay. And the sequence of Sn is called sequence of partial sums. If Sn converges to S, we say that the series is convergent. We say that the series converges and write summation I is equal to 1 to infinity ai is equal to S. Okay. So S is generally called the sum of the series, but to be very precise, it is actually the limit of the sequence Sn, which is the limit of the sequence of partial sums. Okay. So technically, infinite addition is really hard to define, but but if this property holds true, that the sequence converges to S, then we say that the summation converges to S. If Sn diverges, then we say the series is then the series diverges. Then okay. If there is no ambiguity, we generally write shorthand note when there is no ambiguity. Ambiguity, we write summation an for the series. Okay, so I will drop the I is equal to 1 to n or 1 to infinity in to instead write a shorter notation. Then the Cauchy criteria can be restated as follows. Theorem 3.22. Cauchy's criteria. Summation an converges if and only if for every epsilon greater than 0, there exists an n in naturals such that ak is smaller than epsilon for every n and m greater than or equal to n. Or another way of saying it is m greater than n, but that's fine. Okay? Proof is relatively easy. I'm not going to write the complete proof. Note Sn. No, I'm sorry, not Sn. I want An. An is equal to Sn plus 1. No, Sn minus Sn. Sn minus Sn minus 1 with S1 with A1 is equal to S1. Right? In that case, this is literally the definition of what we get for Cauchy's criteria for sequences is. Okay? And so we can fill it, and this directly follows. I'm not going to complete the proof. Three 3.23. Theorem 3.23. Now, the previous one is an if and only if. Okay? This theorem is if then. Okay? if summation an converges, then limit n goes to infinity of an is equal to 0. Okay? Proof? Well, if m is equal to n plus 1, then term 3.22 implies an smaller than epsilon. Okay? Which, since it has to be true for every epsilon, it means that the limit has to go to 0. Okay? Note this is not theorem 3.23 is not an if and only if. An if and only if. Okay? For example, summation 1 over n is equal to 1 to infinity diverges, even though limit n goes to infinity 1 over n is equal to 0. Okay? We won't prove it right now, we'll prove it slightly later. It's a relatively simple proof, but for now, we're going to just state it. Okay? The theorem about monotonic sequences, bounded monotonic sequences, in that case, gives us the following result for series. A series of non-negative terms converges if and only if the partial sums form a bounded sequence. If and only if its partial sums form a bounded sequence. Okay, note. Similar result holds for non-positive terms. Okay, both of these are direct consequences of the results for sequences. Okay. Now we can look at the first result, which allows us to figure out if a sequence converges or diverges, other than what is called the divergence test, which is checking if the limit of sequence terms does actually go to 0 or not. Term 3.25, often called the comparison test. Okay. if absolute value of an is smaller than or equal to Cn for every n greater than or equal to n naught, where n0 is some fixed integer, and if summation Cn converges, then so does summation an. Okay, here it does not matter if an are positive or negative. Even if they were alternating or anything, it still converges. Okay. um, if an is smaller than or equal to dn is smaller than or equal to 0, sorry, greater than or equal to dn is greater than or equal to 0 for n greater than or equal to n naught, for n greater than or equal to n naught, and if summation dn diverges, then summation an diverges. Okay. Now, there is something to note here that I forgot to mention. Starting from theorem 3.4, 3.24 and theorem 3.25, both of these theorems are comparing terms. You can only compare real numbers. There is no order on complex numbers that we have seen, right? We saw the result that the field of complex numbers does not have a total order. So both of these results, theorem 3.24 and theorem 3.25, are only valid for real series. They are not valid for complex series. This is special for real series. Okay? Proof. Given epsilon greater than 0, well, if Cn converges, then there is n naught belonging to n such that n greater than n strictly greater than n naught implies let me call this n1 because I'm going to use it not for something. Such that summation k is equal to n to m of ck is smaller than or equal to epsilon. M greater than n greater than n1 implies, okay, by Cauchy's criteria. Okay, therefore, okay, let me take this n1 greater than n naught. Greater than n naught, such that. Okay. No particular reason. If n1 was smaller than n naught, you can just take it to be n1 n naught plus 1, and it would still work, right? Any bigger n1 works. Whatever n1, there's a minimum n1, but any n1 after that works. So you can always choose an n1 which is bigger than n naught such that this happens. In that case, I get that, well, summation ak n to m is smaller than or equal to summation k is equal to n to m of ck. Oops. Well, by triangle inequality, this is smaller than or equal to ak absolute value, which is smaller than or equal to k is equal to n to m ck, which is smaller than or equal to epsilon. Therefore, A follows. By Cauchy's criteria. Right? Cauchy's criteria was an if and only if statement. So for B, assuming A, if summation an converges, then so must dn, right? Then so must summation dn by A, contradicting its divergence. Okay. Now, the next part we are looking at is called series of non-negative terms. And once again, whenever we are talking about non-negative terms, we are going to be talking about real sequences. Okay? So, series of non-negative terms term 3.26. So there are some series which are used extensively, and the easiest one of them is, I think, geometric series. Okay, so let us look at the geometric series. If 0 is smaller than or equal to x is smaller than or equal to 1, oh, not smaller than or equal to, it has to be strictly smaller than 1. Okay, then summation n is equal to 0 to infinity, x to the n is equal to 1 over 1 minus x. Okay, if x is greater than or equal to 1, the series diverges. Once again, we are looking only at x on the reals, which is why we can look at non-negative terms. Okay. Proof. If x is not equal to 1, we can define Sn to be summation k is equal to 0 to n x to the k, which in that case is equal to the mathematical identity x to the k plus 1, 1 minus x to the k plus 1 over 1 minus x. Okay. Now the result follows from letting n go to infinity. Follows from taking limit n goes to infinity. If x is equal to 1, then Sn is just 1 plus 1 plus 1 plus 1 plus 1 plus 1, and it obviously diverges. Okay. Now, to prove that the harmonic series is divergent, we are going to prove another interesting result first. Okay. Which is theorem 3.27. It says, suppose AI are monotonically decreasing. Okay, they're all positive but monotonically decreasing. Then the series summation n is equal to 1 to infinity an converges if and only if the series summation n is equal to 1 to infinity, 0 to infinity, in fact, 2 to the k ak, k is equal to 0, it doesn't matter, and 2 to the k a2 to the k, which in this case is equal to a1 plus 2a2 plus 4a4 plus 8a8 plus dot 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 converges. Okay. Proof. So this is interesting in the fact that we are skipping a lot of terms. Not every term is being accounted for, right? We are skipping a lot of terms, but the monotonic decreasing allows us to do that. So because this is a monotonically decreasing sequence, I can look at the boundedness of the partial sums. So let Sn is equal to a1 plus a2 plus dot 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 up to an, and let Tn is equal to the partial sums of the other one. So a1 plus 2a2 plus dot 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 plus 2 to the k. So 2 to the k a 2 to the k. Okay. So now for n smaller than 2 to the k, we have that Sn is smaller than or equal to a1 plus a2 plus a3, smaller than or equal to, plus dot dot dot, plus a2 to the k plus a2 to the k plus 1, plus dot dot dot, plus a2 to the k plus 1 minus 1. Right? Well, what am I doing? I have adding extra terms, a2 to the k to a2 to the k plus 1 minus 1, right? And, well, all of these, because of the decreasing property of my sequence, are smaller than a1 plus, well, the first sum is smaller than 2 times a2. The next one's going to be smaller than 4 times a4, and so on, dot dot dot, plus 2 to the k, a2 to the k, which is exactly equal to dk. Okay? Therefore, Sn is smaller than or equal to tk if n is smaller than 2 to the k. On the other hand, if n is greater than 2 to the k, then Sn is greater than or equal to, well, a1 plus a2 plus a3 plus a4 plus dot 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 plus a2 to the k minus 1 plus 1 plus dot 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 plus all the way up to a2 to the k, because, well, n is greater than 2 to the k, so there are some terms that I'm omitting. Well, what I can do is say that this is smaller than or equal to 1/2 of a1 plus a2 plus 2a4 plus dot 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 plus 2 to the k minus 1 a2 to the k. Okay? Because all these terms are going to be, a3 is bigger than a4, so a3 plus a4 is bigger than twice of a4. Well, that is exactly equal to, so not plus smaller than or equal to, this is exactly equal to 1/2 a1 plus 2a2 plus 4a4 plus dot 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 plus 2 to the k ak, 2 to the k, which is equal to 1/2 tk. Therefore, 2Sn is greater than or equal to tk if n is greater than or equal to k. Okay? Therefore, either both Sn are bounded or both are unbounded. Therefore, either both Sn and tk are bounded, or both are unbounded. Now the result follows from theorem 3.24, which talks about series with monotonic terms. Okay? And this gives us a really easy proof for the divergence of the harmonic series, which is theorem 3.28. I'm going to show something slightly stronger than just that the harmonic series diverges. We're actually going to say the harmonic series is a special case of this series and it diverges in this way. Summation 1 over n to the p converges if p p is greater than 1 and diverges if p is smaller than or equal to 1. Okay? Proof. Well, if p is smaller than or equal to 0, this is going to diverge from these terms are going to be more than 1. The limit is not going to 0. So it diverges by theorem 3.23. Diverges by theorem 3.23. Okay. So we are going to assume that p is greater than 0. If p is greater than 0, 3.27 is applicable, which says that, oh, either both of these are convergent or both of these are divergent. And we can look at the series by theorem 3.27. We look at summation k is equal to 0 to infinity, 2 to the k, 1 over 2 to the k to the power p, which is equal to summation k is equal to 0 to infinity, 2 to the 1 minus p to the power k. Okay? Now this is a geometric series, right? Of the form x is equal to 2 to the 1 minus p. Geometric series with x is equal to 2 to the 1 minus p, and hence it converges if and only if, hence converges if and only if p is greater than or equal to, p is strictly greater than 1. Okay? Since the absolute value of x needs to be smaller than 1, right? X needs to be smaller than 1 for this to hold. X is 2 to the 1 minus p. P needs to be greater than 1 for x to have for x to be smaller than 1. Okay? So we are showing something stronger than just the harmonic series. We show that 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1, with equal to 1 being the harmonic case. Term 3.29. If p is greater than 1, the series summation n is equal to 2 to infinity 1 over n log n to the p converges and if p is smaller than or equal to 1, the series diverges. proof, we are again going to use theorem 3.27. Okay, proof. So what we are going to assume for now, even though we haven't completely defined it yet, is that the function log n is increasing. Without proof that log n is increasing. Okay, that's because we have not yet defined log n. Most of you have seen log n before, which is why I'm stating this theorem right now. Otherwise, I'd have skipped it. Therefore, 1 over n log n, it decreases, and we can apply theorem 3.27 to this. It decreases. Okay. Now, note in the theorem 3.29, we are using n log n to the power p, not n to the power p log n to the power p, which would be raising this entire thing, right? So let us try to use let us use 3.27 on my series in theorem 3.27. We get summation k is equal to 0 to infinity 2 to k 1 over 2 to the k log 2 to the k all to the power p. Well, this is equal to summation k is equal to 0 to infinity 1 over, well, by properties of log, this is just 2 to the k log 2 to the p, right? Times 2 to the k, and these two cancel. So this is equal to well, log p to log 2 to the p is a constant, right? So this becomes 1 over log 2 to the power p summation k is equal to 0 to infinity 1 over k to the p. Okay, and now it converges or diverges by theorem now follows from theorem 3.28. Okay, that completes the proof. Note, we can use the same to the same procedure can be continued for example, for summation n is equal to 3 to infinity 1 over n log n. Okay, so let's stop here. Next time we will define the number e, and do the ratio test and other things. Okay. So this is our first one on series.